Okay, to round this unit off, let's talk about assumptions of analysis of variance. So we already mentioned earlier the assumption of independence. That's an important assumption. That's why I put it right in the front of the course, actually. So if you recall, this was about pseudo-replications, about non-independence or partial independence of your observations. So the assumption of independence is a really important one that applies not only to analysis of variance, but to any statistical design. The assumption of normality and the assumption of homogeneity of variances are the other two that apply to parametric statistics. And ANOVA is one of them. So I show you how you can check for assumptions of normality and homogeneity of variances. We'll go over data transformations if your data is not normal. And then I also tell you why you can ultimately ignore those two assumptions. These are actually not particularly important. And if you don't watch this video, so it doesn't have a star, I don't think, if you've never heard of these assumptions, that'll be fine, you know. It makes no difference. And you'll see why. So first, let's take a look at how you can see whether you meet the assumptions of normality and homogeneity of variances. So a common mistake is that people expect their data to be normally distributed just as it's entered in the data table. So if you recall our lentil experiment here as an example, where we have a variety A with a much bigger yield than variety B and C. If you look at your yield column in a histogram, it would probably look like this if you had enough observations. So it will have a bimodal distribution. So soon if you have a strong treatment effect, you wouldn't expect that variable in your data column to be normally distributed, right? And the other interesting thing is that I may still have significant outlier in something like this that are invisible to me. So if I represent some individual observations as point here, for example, I might have a measurement in my sample C that is right on the mean. Or I might have a measurement of sample A that's somewhat above the mean, and for B here I put an outlier in, so that may be 4 standard deviations out, so very unlikely that that is a real value. You know, maybe there was some mislabeling and that is really a variety A plant, for example, so those things couldn't happen. So I have an extreme outlier here with respect to the mean of variety B. Yet in my histogram of my raw data, I wouldn't see that, right? So this would sit somewhere within variety A. I would have no idea that that's actually an outlier. So what you do is you actually work with residuals. So if you recall, what we do in analysis of variance is we subtract the means and divide by the standard deviation, right? So that normalizes my data, and now all my values are expressed as units of standard deviations from the mean. So my green dot now sits right on the 0, and my blue dot here would actually be visible as an outlier. So if I turn this plot 90 degrees to the right and put it on its side, and I take the original units here and make that the x-axis, that's what's called a residual plot. So it's called a residual over fitted value. So that can be original units, but normally if you have other effects in a multi-factor design, like blocks, they usually get slightly adjusted according to the other effects. That's why they're called fitted value, but they are still representing the magnitude of your measurement. So the bigger measurements are to the right and the smaller measurements are to the left, and then your residuals, so how far they are away from the respective mean, those are your y-axis. So again, tracking my points here, my red dot here is a big value, but not too far away from the mean of variety A. My blue dot here is visible as a high outlier, a very large value, especially with respect to the mean of variety B. And then my C measurement here sits right in the middle with a residual of 0. So if I look at my residual plots for the entire data set, this is how I would expect a normal distribution to look like. So if I were to draw a normal distribution on here, it would look like this, roughly. If I have a skewed distribution, my skewed distribution would have the 0 value not centered, but somewhere at the bottom or higher at the top, and I would have a skewed distribution. If I have unequal variances, I would get this wedge shape. So my smaller values may not be as variable as my big values, that can be a problem. And I have outliers again, so this would sit way out here and all my other values are bunched up at the bottom. So those residual plots are really good at identifying problems with your original data. So implementation in R of this is really simple. So you just run your linear model, which does all the calculation of the residuals, and you write this into an output file, and you just plot the residual as a function of the fitted values. So that gives you these kind of plots, and you can inspect them for any kind of problems. So if you find non-normality or unequal variances, you can fix those with transformations of your original data. And usually you have a combination of both skewed data and unequal variances, because the fundamental mechanism that's behind it is that you simply have a few large measurements, and in the large measurements the variability increases. So usually the plot that you see is a combination of both, so they're asymmetric and they have the wedge shape. And those can be simultaneously be fixed with data transformations. So the idea of data transformations is, if x is your original variable, that you transform the axis where the really big values get reined in a lot and the small values are not as much affected by your data transformation. And the typical options that you have are square root transformations. You can take the logarithm or the inverse. So those are increasing in strength. So inverse is stronger than logarithm is stronger than square root. And so the implementation is really straightforward. You just take the square root of your x data. I put a c here, so always consider putting a constant before you take the logarithm or the inverse or the square root. All your values should always be larger than 1. So if you have negative measurement values or values between 0 and 1, add a constant to your variable first before you do the transformations. So either they don't work otherwise, or they behave unexpectedly. And in case of the inverse, what it does is, so big values are going in the denominator, so that means very big values become very small values. So this reverses the order. So if you take 1 minus of that, then your rank order is maintained. So the big values are still the big values. So another thing that you can do with the constants is fine-tune your transformation. So if you find that square root is not quite enough, but logarithm is a bit too much, then you can manipulate the strength of the transformations a little bit. So if the red one is the original distribution, and you shift a little bit closer to 1 by subtracting a constant, or the other way around, if your original values are shifted away from your minimal value of 1, that weakens or that strengthens the transformation as well. So even though I said that it doesn't really matter to do these transformations, they also don't hurt. So by all means, do those transformations. If you can approximate normal distributions better, that's definitely a plus. But the other thing that you also want to do is maintain your original units in your graphs. So there you don't want to show log of yield or something like that with weird units that nobody understands. So instead, just change the y-axis to a log scale. So you can check the graphics labs on how to do that. So you work with your original units and you just specify a log scale and tick marks where you like them in your plots. Okay, so lastly, I do owe you an explanation as to why I think transformations don't really matter all that much, or the violation of assumptions are acceptable even if your data is not normal. And let's do that with a little simulation in R. Okay, let's start by generating some unsavory distributions here. I'm using the gamma distribution function, and we can look at the histogram of this. So that is certainly something that most people would say, oh, you can't use this in an analysis of variance, that really violates the assumption of normality. Sure, that does not look particularly good. Let's do another one like this. So the only difference here is that I add a 4 to have a bit of an effect size, so we can test differences between those two. So this is simply the population 2 here that I generated as the distribution shifted a little bit over. Okay, so let's sample those distributions, which we would normally do. So those are my populations. That's how they are really distributed. And let's use a sample size of 10. And sampling population 1 and 2. And we can look at the treatment effect. Okay. Now let's rearrange this here a little bit. I want to have this on the right side. So this actually doesn't look too bad, but this certainly has a strong skew in it with the median completely off center. And let's bring this into a standard data table. So I'm just naming my treatment levels here, and we can look at the data table. So those are the numbers that I just generated here from my sample, 10 control treatments, and this one here, maybe fertilizer treatment. We can already see this does not look very good. We have some big values and then a lot of smaller values. But nevertheless, let's run an analysis of variance. And how nice, we just get a significant value here, just based on alpha of 0.05. Now, one thing we can do is we can run a permutational ANOVA. We haven't covered that yet. This will come in one of the next labs, but for now, just accept that this one works completely differently, and it doesn't have the assumption of normality at all. So let's run it, and look at this. We get exactly the same answer. So by that measure, it would be hard to make the case that analysis of variance doesn't work, and you really, really have to use this, otherwise you're out for lunch, right, with those distributions. So we don't actually need permutational analysis of variance. You can just stick with the normal procedures, even if your distributions are crazy. And maybe that was a fluke. Let's do this again. So I'm just running this here from taking the sample. Let's take the sample first. Well, that one has a outrageous outlier here. Okay, so let's run those two. And we get 0.011 versus 0.010. So almost no difference, right? Let's do it one more time for good measure. So this time, it's no difference at all, no significant difference. And so it never ceases to amaze me how variable those individual sampling runs are. So also this simulation shows that the reliance on the p-value is really completely nonsensical. So I can't emphasize enough, and I've done it a couple of times already, what you always want to work with and what you always want to use for your inferences are confidence intervals and effect size statistics, right? So I showed you how to do it in the last lab, and we'll also cover it again very carefully in this lab. So these are buffered against these uncertainties, against these runs. These p-values here are not buffered against those sampling uncertainties, right? So one sample, you have a small variance and a big effect, and you get a highly significant p-value. Another one, your variance may be quite large, and your effect size smaller. So these are really raw, unbuffered statistics that you can't rely on, right? So you need to work with intervals that convey that uncertainty, right? That's what they are there for. So if you wonder why that is, that the assumption of normality in most cases really does not matter, you just have to think back about the fundamental principles of statistical inferences that we covered. So if you recall, the population for us is in a black box, right? We normally don't know the distribution at the means of the population. So we just take a sample, and that sample here jumps around, just like we've seen in that simulation that we just did. And so what statistical inference is based on is then the imaginary distribution of those means, right? And those are actually normally distributed, even if your original population isn't, right? So that was the concept of the central limit theorem. You can also remind yourself or try this out. As soon as your sample size is reasonably large, so 10 is plenty, that distribution of the means from which I actually calculate the p-values, that is normally distributed. So that's why it works. So the only instance where you might want to be a little cautious is if your sample size is really small, like 2 or 3. But even in that case, your p-values are still comparable to non-parametric statistics, to modern non-parametric statistics, I should say. And so that reminds me of a last thing. So if you come across somebody who asks you to statistically test for assumptions of normality, that really is the stupidest thing that was probably ever thought up in statistics, because if you want to demonstrate a significant departure from normality, you need a rather large sample size, right? So in that case, the assumption of normality really doesn't matter. And if your sample size is really small, then your statistical test for departure of normality will certainly say it's not significant. But actually, in that case, you might want to worry a little bit. So tests of assumptions of normality you can completely forget. There really is no scenario under which those give you any kind of information that's useful.